second session of NetCompute workshop. Our first speaker today is Jan Rüth. I'm sorry for my poor German pronunciation. Jan is a fourth-year PhD student from RWTH Aachen University in Germany, and his research interests center around network measurements and transport protocols. Thank you very much.
Thanks for the introduction. Yeah, so this joint work with my colleagues René and Klaus from Aachen and Vedad and Sandra from Control Theory of TU Munich. And it's probably a bit different from the talks you heard earlier on, but I think it's very much in light of our initial keynote today. And it's about moving control into network elements, and especially industrial feedback control. And to get started, what actually do I mean by control? So control processes are quite ubiquitous to us. They're all around us, but we typically don't notice them as being control processes. Control processes that you might know are, for example, in your car. You have a cruise control in there, so when you're on the highway and you want to go in a steady speed, you can simply tap on a button and it goes in a steady speed. So there's a control process involved in this that makes your car accelerate or decelerate. And there are other more fancy control processes in more modern cars that can follow other cars, speed up and whatever. Another thing that you probably know is autonomous drones. They stay in the air. You can push them, they go back to the original position. There's also a control process. The most famous one is probably the Segway, so you can stand on it, and if you lean forward, there's a control process that wants it to be stable, so upright, and thereby it goes forward. These things are also used in industry. For example, if you manufacture some goods, here's an example of car production. The robots need to interact, for example, with humans, but also with each other, and they need to fit products into the car, and you need control processes for that. Something else, if you want to have two robots that pour a glass of beer, you also need control processes because you don't want to have too much foam and whatever, and you want a nice control of that. And actually, in production today, these control processes, they carry out through many different stages in there. These things typically work like this. You have a physical system, so for example, our two robots pouring in a beer, and you typically sample the physical state of the system with the help of sensors. Then these sensors transmit typically, or in our case via a network, they are signals to the controller, which is simply put like a computer that takes these as an input and produces an output with which the system can be put into a different state. So, for example, with our robots, you can move the arm, for example. And you typically also do that via a network. And, well, if you want to do this, this works, but imagine in the future, the factories that people want to build, they should be very flexible. That means they want to produce one good today and maybe another product tomorrow, which means they also need to interchange all of this. So the system changes, the sensors changes, and thereby also the controllers need to change. And this is a quite costly process. Therefore, control research actually suggests to just outsource all that stuff to the cloud, because from us, they know the clouds are scalable, they're elastic, they're nice for this kind of stuff, which is kind of true. However, if you look at how that control actually works, this is maybe not the best idea, because if we put the controller in a cloud, we'll put the public internet in between. And there's only best effort in there. So actually, we'll have a lot of, we'll introduce a lot of delay, which is very bad for control process, as I will be showing you. This delay, you can account for it to a certain degree within your controller design. However, it's something that you want to erase. It might make sense to move control synthesis to the cloud. So for example, if you have a lot of measurements, you can derive new controllers from that. But the actual control, you don't want to have that there. So what we wanted to explore in this paper is basically, is it possible to implement a controller that, for example, these two robots or the Segway, can we implement that in a network element? And further, can we implement this with the data plane language that we know like before? The scope is basically, can we move the control logic back from the cloud to the local network elements, thereby skipping unpredictable latencies. So imagine there's a controller sitting in the cloud. Can we move parts of the processes, for example, to the local switches of the factory again? So thereby we can use the existing network infrastructure within the factory without deploying new hardware. So we can have all the nice cloud properties like orchestration from there and leave the synthesis there, but skip the bad latencies of the internet and reuse the network infrastructure. Well, you might ask, what is a controller physically? So what are we actually moving? To explain this, let me go a step back and tell you how control works a bit on a high level. Basically, you can split the control into two phases, an offline and an online phase. And assume we have this physical system. So we have got a robot with a rod on it. It can rotate. And we want to balance this glass of wine on top of it. What you do is, in an offline phase, you get someone who's good in physics to describe the physical dynamics of that system. And you typically do that by a set of linear differential equations. And because all our systems here are digital, it's typically a set of linear difference equations. And then you get somebody from control theory and apply control theory, which is something like this. So there are different controllers, for example, PID controllers. They have also been used for example, for TCP congestion control. There are other things like Kalman filters or neural networks, but we'll be focusing on linear quadratic regulators, which is a class of controllers that is known to be optimal for certain problems. And they're already kind of advanced. So people tend to use PID controllers very often because they're even simpler, but we focus on LQR. And the output of many of these controllers is simply a matrix. And with the help of the matrix, what you can do is basically, in an online phase, you simply multiply the current system state, so whatever you sampled with your sensors, with a matrix, and you get an output which you need to apply to the system. And this is the part we actually want to move. So it's basically a matrix multiplication that we want to embed into our network, which does not sound to be too hard, right? And now is the part, if you didn't like control, you may wake up because now the networking part comes in. So in the first shot, we implemented this controller in BPF. If you don't know BPF, that's this Linux in-kernel network, in-kernel virtual machine. So we can deploy it on Linux switches. And that's nice. We also have a Metronome SmartNIC where this runs. And it's basically writing C code. So a matrix multiplication in C isn't really hard. So it can pretty easily be done. The next question we had is, can we do it in P4? And you might have also heard that earlier. P4 and also BPF, they're not really good at math and other things. We already heard they only support integers. So depending on the platform that you have, and you get different bit depths, you get different padding, different operand support. The problem is all the control problems are typically specified over real numbers, so floating points, which is bad because we can't directly use them. So, well, it's not a real problem because we can simply, for example, scale all our real numbers with a fixed point, so a very large number, and then we just take everything before the decimal point, and then we have integers. However, if you do computations now with fixed point numbers, you need to account for fixed points, for example. So if you multiply two fixed point numbers, you accidentally scaled all your numbers by the square of the fixed point. So you need to divide by the fixed point again. And all this multiplication, they can easily overflow the bit depths of your integers. And as it turns out, if you try to implement this, you will find, oh, P4 isn't even specified for negative numbers. So if you want to do divisions on them, which is odd, at least to me. So you need to account for all of this. And in our implementation, what we basically did is we have our controller. It is synthesized, and we basically represent it as something that we store in the tables, just as you would store flow mappings in a table. So it's basically just for numbers in the example that we will be using. So you need to implement a 1/4 matrix multiplication, which isn't too hard. So the LQR controller is basically K. So what you need to do is you need to compute minus K transpose times U, and U is your sensor reading, which you get via the network, which doesn't sound too hard. If you implement this in P4, it becomes a bit ugly because, so we assumed all our numbers are 32 bits, and because they can easily overflow, we enlarge them to 64 bits. We do our matrix multiplication. However, because we assume fixed points, we need to scale by the fixed point. And well, we can't do divisions on negative numbers, so we need to branch here. And because we can't do divisions on signed numbers, we need to convert them to unsigned numbers, do the division, scale them back to positive, or scale them back to the negative number, and do all the bit stuff. So it works, but it is pretty ugly somehow. So if I would need to program that on a daily basis, I wouldn't like that, because it just doesn't feel right. Then we took this implementation and, well, together with basic switching functionality, described it in a P4 switch representation, and we again compiled it to BPF, because we can flexibly implement that on our smart NICs. And for that, we use the P4C XDP compiler by VMware, and we use this simple testbed. So on the right, we have a control process, so something physical that we actually want to control. In the middle, we have a switch, so a Linux switch, to which we either offload our program. So it contains a Metronome smart NIC, so we can offload it to the smart NIC, or some virtual Ethernet device if we want to run all of that in a mininet, for example. And on the left, there's the controller. So this sits in the cloud, so to say. So that link we can simply shape with a lot of latency if we like, or some latency. For the physical process, we use a real-time simulation of an inverted pendulum. The inverted pendulum is basically the textbook example that they use in control theory to describe physical systems. It's basically the Segway example. So the idea is you got a card, and on that card you install a rod, and it can move freely 360 degrees. And there's a little mass on top of it. And the goal is basically balance it in an upright position. You can do that by moving the card to the left or to the right. It's basically like balancing a pen in your hand. So if you ever did that, it's quite tricky. It gets easier if the stick is longer, but you can do it. And the sensors, they basically acquire the current position of the card, the change in position of the card, the angle of the rod, and the change in angle. And well, as I said, we can move the card. So we implemented that. We have a little visualization of this, and basically here you can see the card is the black bar on the bottom, and then we have a rod and a little mass on top of it, and this shouldn't happen. So there's no control involved. It will simply fall down, and well, if that was the glass of wine example, your floor is now spilled. And this is what should happen. So the card should be moved to the center, basically, and thereby flipping the mass on top of it, and well, it stays there and is steady. Typically, to measure how good your system is, in control theory, you measure the quality of control, which can be quite different for whatever you want to measure. But basically, for this example, what you want to measure is how fast can we move the card to the center? So this was the goal, move it to the center. And how stable is the rod around its upper position? Well, for a baseline, we basically took our setup, we assumed no latency anywhere, and the control is done by the controller. And what you can see here is basically a plot of the position of the card as well as the angle of the rod. So the blue line is a position, and on the top is the absolute position, on the bottom the relative position to its goal. And what you can basically see is a smooth transition, as you saw in the video 2 slides earlier. And after roughly 4 seconds, the card has moved to its position, and the rod is stable around its upper position. So, and you can see basically the lines are pretty smooth, so everything is quite nice. Things change a bit if we add just 5 milliseconds of round trip time. So what you can see here, this is what happens. In the beginning, you can see is that the card moves forward and backwards. It starts wobbling around, and after roughly 1.5 seconds, you can see it loses control over that thing. It starts to rotate freely because basically the measurements from the sensors, they come in too late, and as well the actuation commands, they come in too late. So basically, it's getting more energy, and it starts to rotate, which isn't good. So if that were deployed in a factory, you wouldn't want that. Well, in control theory, you can account for this stuff to a certain degree. So in this example, you use 20 milliseconds of round-trip time, and we modified the controller such as in the initial design, we know that this might happen. And then you get this. So what you can see is basically, in the beginning, it moves a little bit back and forth, but eventually it stabilizes again in roughly 4 seconds. However, if that was the example with the glass of wine earlier on, it might probably still spill because it wobbles. So we further modified it to not do that in the start. However, then we couldn't get it to eventually to stabilize within 4 seconds. So both are not optimal because we can't simply design a controller that gives us the same quality of control as if there were no latency. However, we can have close to no latency by offloading that stuff into our P4 switch. So we offloaded the controller that I showed you earlier into our Linux switch, so basically bypassing the latency, and this is what happens. So basically, again, what you see is it looks like the initial example without any latency, because it basically is the initial example without any latency. Our implementation of the controller is basically just like the real implementation, so you can't see a real difference. There's no initial wobbling, and it again stabilizes within 4 seconds. Okay, this sounds as if these problems are pretty easily solvable in P4, right? However, there are some cases where all of this breaks. So future challenges are, for example, one would very much desire to change tables from the data path. Because if you would like to account for delay, what you basically do is you bloat all your state spaces and need to save past measurements. So what you would need to do is you would need to save your current computation and put it into a table. This is currently not doable with P4. You could do it with BPF, but also on our SmartNIC, you can't do it. Another thing, network control is actually only, so you can do simple control tasks, as I just showed you, but it actually is pretty good if you want to do collaborative control. So if there are multiple robots involved that need to interact with each other. So to do this, what you also need to do is you need to share past measurement data with your other controllers. So if you implement these controllers in the same switch, it's okay. It basically boils down to the first problem. However, if they're on different physical entities, you need to exchange packets. And I'd argue it is not enough to do that from the control plane. What you actually would want is to generate packets from the data plane. So P4 doesn't really say anything about that. The new portable switching architecture state that it might be possible, but this is problematic. But there are other instances of control that might be more challenging. For example, audio processing is heavily used in industry. One thing that they do is they measure the vibrations, for example, of some machines, and these vibrations, they change once, for example, they wear out and they need to be maintained. However, if you want to do audio processing, for example, in a network element, it needs to be done over many packets because the data is just too large, which could also be very challenging. And the same is true for visual processing, which is also heavily used, for example, to find defect goods and then in a second iteration track them on, for example, a conveyor belt and have a valve with some air throw it away. And they have many packets and you need to basically store this information in between. And this computer vision algorithms in itself, they might also become very heavy. So to conclude, our initial question was, can we implement a controller in a network element, and can we do it with a typical language such as P4? The simple answer is yes, you can. However, math is pretty much a hassle in P4, and advanced problems currently lack functionality in that language. And, well, what other tasks could we offer? So this is pretty much a non-networking task that we actually offloaded. So what other tasks are there that are not typical that you would think about that you could offload? Thank you.
Thank you, Jan. Do we have any questions? Thank you. Do we have any questions for the speaker?
Much of this work, as I understand, was motivated by the big and unpredictable latency and maybe unreliable delivery of the network between the controller and the controllable device. Could we solve this by adding a small compute node on the next to the switch that could do most of this math and some advanced functionality just closer to the device?
Definitely. So it might depend on the actual task. So if you add another computer there, you need to make sure that the packets get off the wire quite fast and that you don't introduce delay from things like interrupt coalescing or something like this. It depends on your actual system. So depends how much is the sampling frequency, for example, of your sensors. Can a regular PC sustain that? But definitely, I think you could add a PC that does that. But yeah.
Thank you.
Are there any other questions? Okay, then let's thank the speaker again. Okay. Our next speaker today is Davide Sanvito, who is getting his PhD at Politecnico Milano. He works in the ANT group at Politecnico Milano, and his research interests are in software-defined networking with a focus on stateful data planes and traffic engineering. He spent his last 6 months as an intern at NEC Laboratories Europe in Germany.
Tranquillo.
Does it work?
Yes, I hope so. We have this change. Okay.
Sorry for the delay. Okay, so artificial intelligence is nowadays a very hot topic. In particular, deep neural networks are obtaining outstanding results in many topics. A neural network is a machine learning tool inspired by the human brain. Sorry. And the neural network is made of is a sequence of interconnected layers of neurons. Neuron is the basic unit. A neuron receives in input the different signals from other neurons. These signals are called the activation of the neurons. Then it applies an ordinal function to produce an output which is received by other neurons. The hyperparameters of the networks are the number of layers, the number of neurons per each layer, and the type of layer. For example, fully connected layers are made of neurons, which receives as input the output of all the neurons of the previous layer. A multilayer perceptron is a neural network all made of fully connected layers. There are other types of neural networks, such as convolutional neural networks, which introduces other types of layer, for example, pooling layer, convolutional layer, or normalization layer. In order to be able to use a neural network, we need to train it. So we need to use our data to understand which are the proper parameters of the interconnections in order to perform the task, for example, a classification task. This process is computationally heavy and it's usually performed offline. Once the network has been trained, the second phase is the so-called inference. In this case, we are given as input a new data and we want to obtain a prediction as output. This phase is much lighter, computationally speaking, and it's usually performed online. In some applications, we can have some constraints on the latency of this process. Since these processes are very computationally heavy, the community has introduced AI accelerators, which are devices used to speed up the execution of the neural network. The first category is the general purpose GPU. These devices are able to perform parallel computation on a large amount of data, and they are particularly efficient when operating on big batches of data. In order to be able to use the accelerator, the data has to be moved from the CPU to the GPU. And this can introduce an overhead in the final latency. For this reason, those devices are usually best suited for the training phase. But in case of neural network inference with latency-sensitive services, usually the inference is performed on the CPU. Another category of accelerator is made of custom ASIC, which are dedicated to the neural network inference, like the TPU developed by Google. Also in this case, depending on a particular architecture of the network, the data transfer to the accelerator can introduce this movement can constitute a big amount of the processing time. In this paper, we are exploring a third possibility, which is the use of programmable network devices. Those devices, such as smart NIC or network switches, nowadays can do much more than pure forwarding. They are able, for example, to execute logical and arithmetical operation on the data, which is read from the packet or from the local memory of the devices. If we consider an end-to-end system where the inference requests are received from a front-end server but processed by a back-end server, these devices sit in a privileged position to perform processing on the data while it travels in the network. The main contribution of our work is to profiling the execution of the neural network inference on a CPU and to analyze which are the characteristics of the processing computed by the different types of layer. We also analyzed which are the options to split the execution on different executors. And finally, we understand under which condition we can use network devices to perform part of the computation of the neural network inference. In our work, we focused on convolutional neural network, even if those kind of networks represents the smallest portion of workload. The final part of a convolutional neural network is made of fully connected layers. So by profiling convolutional neural networks, we are also able to understand the characteristics of multi-layer perceptron. In particular, in our work, we focused on AlexNet, which is a convolutional neural network used for image classification. We can see that there are different types of layers, like convolutional pooling layers and normalization, but the final part of the network is made of 3 fully connected layers. The first analysis we performed is a static analysis, so just by observing the architecture of the network without running the inference. We computed which is the output size of each layer. We can see that in the first part of the network, the output size is comparable to the input size of the images, while the second part, the one of the fully connected layer, has an output size which is much smaller than the first part. We can also observe that some layers, like the convolutional one, increase the data compared to the input size, while some other, like the pooling layers, reduce the dimension of the data. In the second picture, we analyzed the number of parameters, so the number of weights used by the different layers. We can see an opposite trend here, because in the first part, the number of parameters is much lower compared to the second part. The very high number of parameters of the fully connected layers are due to the very dense pattern of the interconnections. The second analysis we performed is the runtime analysis. So we consider a dual socket NUA machine with 2 Intel CPUs. We use the Intel Caffe as a machine learning framework, and we run the inference using a single isolated core on a dedicated CPU. We measured the total and the per layer inference latency, and at the same time we collected hardware counters using a Linux perf tool. These counters were collected every 10 milliseconds. In particular, we collected instruction per cycle, the number of stalled cycle, and the number of cache misses on the different levels of the cache hierarchy. So we executed the inference of some images, and we can see in the first picture the different contributes of the layers in the total inference latency. We can see that the biggest contribute is given by some of the convolutional layers and some fully connected layers. By looking at the time evolution, by looking at the values of the hardware counters over time, we are able to characterize the different type of processing computed by the different types of layers. In particular, we can observe that in the first part of the inference, so the one related to the convolutional part, the IPC is very high. So you can conclude that the processing of the convolutional layers is computation bound. In the second part, so in the fully connected section, we can see that IPC drops to around 1. It is motivated by the very high number of stalled cycle, which is due to the very high number of parameters which has to be loaded into the cache. So we can observe that fully connected layers are characterized by an opposite behavior. So this processing is memory bound. So if we were able to move the execution of the fully connected layers to another executor, we might be able, on one hand, to reduce the inference latency, and on the other hand, to free some resources of the CPU, which can be used for a kind of processing which is better suited for a CPU. We try then to evaluate which is the impact of a splitted execution of a neural network. We considered two scenarios. We ran 2 instances of Intel Caffe, each one executing a portion of the neural network. And in the first scenario, we moved the intermediate data using the QPI connection, while in the second scenario, we forced the intermediate data to be sent over a TCP connection over a loopback cable, because we wanted to assess which is the impact also on the communication of this data over the network. Oops. Okay, sorry. Okay, so in the picture, we analyzed which is the increase of the inference latency compared to the non-splitted execution, and we tested this increase for different splitting points of the network. In the white bars, we can see that the increase in latency can reach up to 8%. But the increase depends on the size of the output data, of the intermediate output data of the different layers. So we can see that if we carefully select a proper splitting point, this contribute can be very small, can be kept low. On the other hand, we can see that in the second test, so the one where the data is transmitted over the network, the increase is much bigger, between 3% up to 12%. However, if we were able to execute part of the neural network in a network device, we would be able to avoid the extra cost of data movement, because the data has to be transmitted in any case to the network. So we proposed our scheme, which is banana split, in which we split the execution of the neural network. In particular, the first portion is executed by executed on a CPU up to the fully connected layers. The intermediate result is then encapsulated in a packet, which is then transmitted to the network card. The second portion of the network, so the fully connected layers, are executed on the network card or on the network devices, and the final result is then written into the packet. In order to be able to execute a neural network on a network device, we need to employ neural network quantization techniques. These techniques allow us to reduce the number of bits used to represent the data and the parameters, and allow us to reduce the amount of memory required to store the parameters. In particular, we adopted the extreme case of quantization, which is the binarization. In this case, the activation and the parameters request just 1 bit, and recent research have shown that it's possible to highly reduce the memory by keeping a limited drop in the accuracy of the classification. Once the activation and the parameters are represented with 1 bit, the execution of the neuron just require bitwise logical operation and the pop count. And these operations are supported by the programmable network devices. In our proof of concept, we extended N2Net, which is a previous work from some of the authors, and we added the support for the SmartNIC. N2Net is a compiler that, given a description of a binary neural network, is able to provide a P4 program to run the binary neural network on a RMT-like pipeline. In our extension, we replaced the pop count implementation with the one provided by the SmartNIC. At the moment, we still don't have the full end-to-end prototype, but we evaluated a micro benchmark by implementing a single binarized fully connected layers with 4,000 neurons, which is the exact size of the biggest fully connected layer of AlexNet. This layer binarized as activation and output around 500 bytes, which fit the network packet. So we are able to read the input of a neural network and of the layer, and to write the output in the packet using P4. And the parameters of the layers are pre-configured in the memory of the SmartNIC. Under this configuration, the execution of the single layer takes 1 millisecond. So in conclusion, we analyzed the suitability of the programmable network devices at their current state to be used as a coprocessor for neural network inference. Our scheme split the execution just before the fully connected layer. In this way, we are able to take advantage of the processing of all the components of our system. By offloading the computation of fully connected layers to another executor, we can free the CPU for a kind of processing which is more compute intensive. And since the contribute of multi-layer perceptron in a
data center is very high. By freeing this workload, we are able to increase the overall efficiency of the infrastructure. This work is still in a preliminary stage. There are some open points. The accuracy of the final system depends on the accuracy of the quantization techniques, which is still an open research problem. And the second point is that since we are moving parameters into the network devices, we need to share this memory with the conventional network functions. However, if the memory becomes scarce, we can think about allowing multiple splitting points into the neural network, and so we can distribute execution on multiple devices on path. Thanks.
Do you have questions? Really interesting talk. I had a question about the prototype on the SmartNIC. Did you make any use of the possibility to map the network, the source neural network, to a topology, to a network on the SmartNIC itself, right? So I was wondering if there is any optimization that you've exploited in carrying this out.
Sorry, any optimization
that you might have used, because you start with a network, but on the SmartNIC, depending on the SmartNIC that you use, you also have a network of, for example, in the metronome cases, you have a network of micro engines. Mm-hmm. And I was wondering to what extent your implementation might have used that to maybe map a set of neurons to a micro engine and use a division of labor of that.
Actually, we are executing different portion of the layer on different on different island in order to be able to parallelize the execution. Exactly.
Thanks.
Yes.
Thank you for your talk. My question is, why do you just split the neural network to two parts, to two portions? Do we need any further split in a more fine granularity manner?
Yes, it's possible to use the different many splitting points. For example, if the memory of the network devices becomes a concern because we need to share the memory with standard network functions, it's possible to think about allowing multiple splitting points because we have just to take the intermediate result from the packet, compute the layer, and then we can copy back the result to the packet and then send the packet to the next device on path. So it's possible to split layer by layer the execution potentially. But we don't want to, we cannot split the layer in the middle. We have to provide the intermediate result, which is the proper size for the next layer. So, I mean, the minimum granularity is the layer in our case.
In that case, we should also consider the principles to assign different layers to different devices, right? Mm-hmm. So what's the important principles?
What's important, sorry?
To assign different layers to devices.
It depends on the available...
How to assign?
It depends on the available memory and also on the path the packet has to travel to go to the destination. I don't know if I replied.
Thanks.
Thank you for the talk. As I understood, in order to feed these fully connected layers into NIC, into this smart NICs, you use some quantization techniques to reduce the memory footprint. Is this right?
Exactly, yes.
I wonder if you try to apply the same techniques but keep the layer on the CPU, whether it would shift the bottleneck
yes,
from...
Yes, actually, we tried. We have a slide. So if we execute the binarized version of the fully connected layers on a CPU, we can actually save a lot of time and the computation, because the latency is reduced by 80% of time. But still, since the workload quota of multi-layer perceptron in a data center is more than 60%, if you are able also to offload this small portion, we are saving a lot of resources. But yes, quantization also increased execution on CPU.
Thank you. That's interesting.
Change the resolution.
Yes, well, this one.
It should be working this mode.
Yeah.
Our next speaker is Theo Jepsen from the University of Lugano, where he has an incredibly handsome and intelligent advisor. Theo has his undergrad degree from Cornell University, his master's degree from University of Wisconsin, and he's interested in data plane programmability.
Okay, so
as you can tell from the title, this is about concurrency control. So why do you need concurrency control? Imagine that you and your spouse both have a shared bank account and both of you want to add or deposit $100. If both of you do this concurrently, then you'll execute the same transaction, 50 plus 100, and the resulting balance will be 150, but it should be 250. So this is not correct. What you can do is you can use pessimistic concurrency control, and with this, when you execute the transaction, you get a lock, and after you acquire the lock, you increment the balance, and then the other person can get a lock afterwards, or even concurrently, and increment the balance, and then we get to 250, which is what you'd expect. But locks are expensive because you have to acquire the lock and then release the lock. We can do better than this using OCC, or optimistic concurrency control. With OCC, you read a value from the store, or the data store, or the account balance in this case, and you locally execute the transaction, so 50 plus 100, and you use a guard. In this case, you say, if the balance is still 50, then increment the value to 150, and it works. If the other person executes the same transaction at the same time with the same guard, this will fail because the guard is no longer valid. The other person assumes that the balance is 50, which is not correct. It's actually 150. So this transaction is aborted. And this person retries the transaction with updated value as a guard, 150. And this time, the transaction passes because it matches the current value in the store. So what's the difference between pessimistic and optimistic concurrency control? Which one's better? Can you say that optimistic concurrency control is always better than pessimistic? So some people say that pessimistic is better. This is what Stonebreaker says at least. And other people, in this case, Theo says that OCC is better. And Franzik and Robinson also say that OCC is better. But more recently, a landmark paper from Argowal and all say that it depends. There are multiple factors which have a role in the performance of OCC and pessimistic concurrency control. And what we focus on in this work is looking at contention. And by contention, we mean the number of clients or the number of transactions that are being executed in parallel. And there's a trade-off, it turns out, that when there's low contention, that is few transactions being executed in parallel, which touch the same data item, then pessimistic doesn't do so well. This is because each transaction needs to acquire a lock, and this is acquired, you could say, unnecessarily, because the transaction could have been executed without acquiring the lock and have succeeded and update the value correctly. But for optimistic, low contention works well because since you don't need to, it's unnecessary to acquire the lock, then you're just executing the transactions without any overhead. However, when you increase contention, so if you have multiple transactions executing concurrently on the same item, then pessimistic does better. This is because the locks are not a waste of time. This is because every lock you get ensures that you're not going to conflict with another transaction and not going to pay the overhead of doing an abort. However, for optimistic concurrency control, it's not, high contention is not so good. This is because there are lots of aborts. So as we saw on the previous slide, when a transaction fails, you have to retry the transaction until it commits. And if this happens multiple times, the store spends lots of time, wasted time, trying to commit a transaction, only to have it fail and retry again. And these aborts, these retries, that's what causes the performance to degrade. And this bottom right corner, optimistic for high contention, that's what we'd like to improve with this work. So what's going on in that corner with optimistic and high contention? We did a simple experiment to see what's going on as you increase contention. So what we did is we had some clients execute the transaction we saw before, incrementing a value, and we increased the number of clients, which increases the amount of contention. And as the contention increases, ideally what we'd like to see is a constant throughput, so that there's no effect as you increase the clients. There shouldn't be a degradation in performance. But actually with OCC, what we see is that more clients causes more contention, which causes more aborts and lowers throughput. And in this case, it lowers it significantly compared to the ideal. So what's going on there is that the store is spending lots of its time, wasting its time processing these doomed transactions that won't commit because we know that they have invalid guards. But what if we had infinite number of CPUs to process these transactions that are invalid? If we had these infinite resources, then maybe we could just spin and execute these wasted transactions. And since hardware can execute these transactions very quickly, maybe that would be some way of doing it. And since there's hardware now that's sitting in the network, programmable switches, maybe we can use that to offload these transaction processing. And maybe we can done in a speculative way. So that's how we came up with NOC, Network Optimistic Concurrency Control. With NOC, we offload the transaction verification processing to the switch. These are network switches that are sitting in between different devices in the network, between clients and the data store. And what NOC does is it allows for high parallelism for high contention workloads. This is done by, instead of executing the transaction verification at the store where the data is stored, we execute this verification in the switch, in the network. And this, in turn, reduces the server load for the workload. At least it reduces the load at the end host. And we found that it increases the performance for end-to-end performance for workloads like TPCC, which is a OLTP benchmark. So how does NOC work? First, let's look at the system model. So we assume that there are multiple clients, and each client has a local cache. And the clients read from the store. They update their local cache with values they get from the store. And then using these values, they can execute the transactions locally and then submit them to the store. And this is done using, as I mentioned before, a guard and what we call a comparison, where the client compares the value that's in the cache, its local cache, to the value that's stored at the store. And if that value is the same, then it's up to date with the store, so the transaction should commit. So it can send a compare along with a write. If the comparison is valid, then the transaction should be valid according to the store and commit. And we extend this with NOC running on the switch. What we do is we add a cache on the switch, not a read cache, but a write cache. So when the client executes a write transaction, we update the cache with the value that's being written. Then, if the store were to abort a transaction, we also update the cache with the value that that's contained in an abort message, which indicates why the transaction failed. This way, when a client goes to send a transaction that's guarded with a comparison, if the comparison is invalid, instead of sending the transaction to the store to be verified and committed, the switch can speculatively abort this transaction. And because it knows it's seen previous values, and it knows that this transaction will never abort at the store, so there's no point in forwarding it to the store only to have it executed and aborted at the store. So let's see an example of how this works. Let's say we start off with the clients reading values in the store and updating their cache. So on the left, we do a read. We update the cache with the balance, which is 50. Then we send a transaction. I assume that the value is 50. Assuming that, write 150. So we're incrementing the value. And this goes through and everything works fine. We update the value to 150. Now another client, which also did a read, but this read was done before the store was updated. This client sends a transaction, an update transaction, but here the comparison is invalid because the comparison is out of date. Here the client says, I assume the value is 50, then update to 150. The store, as you can see, the switch sees that the comparison is 50. It compares it to its local cache. They don't match. So the switch, instead of forwarding the transaction to the store, it does a speculative abort. It knows that this transaction will never commit at the store and just responds immediately to the client. This way, as you can see, we don't have an extra round. We reduce the end-to-end time for aborting this transaction. Instead of having the transaction go all the way to the store, back to the switch, then back to the client, we just respond immediately with an abort. And this abort contains the latest value that the switch has seen. This way, the client can re-execute the transaction immediately. The benefits are two. As I mentioned, it reduces the round-trip time for aborting a transaction. And apart from that, you can notice that this verification, the verification logic for aborting this transaction is not executed at the store, but it's executed on the switch in the network. And this offloads the computation from the store, which probably is running on a commodity server using a CPU, where the cost of verification is higher, compared to doing this in the network using some logic which can be executed faster at a lower cost. And by lower cost, I mean fewer cycles. I'll show you more detail on how we do that. So you may be thinking, there's a cache in the network, and we're aborting transactions, and I use the word speculatively. So what about correctness? So NOC guarantees strong consistency, and this is because the cache is only used for writes. The cache will never service read requests, so clients never read stale values from the cache. And because the cache is updated both by the clients when they do a write and the store when the store sends an abort, this means that eventually the value that's stored on the switch will be up to date, so transactions eventually will commit. And this means that we have liveness. So how did we implement this? We use P4 to implement a switch prototype running NOC. And it wasn't so straightforward though. As you may have heard today, when you're writing these things in P4, there's some things that you have to work around. And this is a challenge, but what we get out of it is high performance. So what we had to deal with was storing these cache values on the switch somehow, and then also processing transactions. And the transactions that we're processing, they're composed of multiple operations. A transaction is sent to the switch as a packet, and this packet contains multiple operations: a read, a comparison, and a write. What the switch has to do is parse out each of these transactions and check, first of all the comparisons. If each comparison in the packet is valid, then it can check all the writes. And for each write, it updates the cache. It updates the values that are stored on the switch. You may know that P4 doesn't provide any looping primitives. In C or Java, Python, you can do a for loop. But in P4, there's no such way to do this. So what we have to do is recirculation. We recirculate the packet through the pipeline, and on each recirculation, we process one of the operations in the packet. Since a packet can contain a variable number of operations, we have to do a variable number of iterations through these, or variable number of recirculations. Loop unrolling is not an option since we don't know how many operations the packet may contain. And then, as I mentioned, another challenge is storing the values on the switch. Because the values are 128 bits, we can't store the entire value within a single register. So what we have to do is we have to split the single value into multiple registers. We shard the value across, in this example here, 4 registers. So the first register contains the first 32 bits, the next 32 bits, and so on. So we store the values on the switch and not version numbers, and we do this because clients don't know what the version numbers are when they submit transactions. The switch doesn't know them either. So we use the exact values instead of version numbers. So after we implemented this, we wondered, how does it perform? So we did some micro benchmarks as well as evaluating it on some benchmarks like TPCC. Let's start off with the micro benchmarks. So what we did is we set up a client and a store, and in the middle we had a Barefoot to Fino switch running our P4 program. And the micro benchmark in this case was, as we saw before, incrementing a value. One or more clients are trying to increment the same counter that's stored on the store. So for the micro benchmark, we found that NOC has higher throughput than using OCC using the store alone. And as the number of clients increases, the contention increases. And as we saw before, the throughput for OCC degrades. However, for NOC, the performance remains higher. And it does degrade a little bit, but as we can see, it plateaus a lot higher than OCC does. And then looking at latency, what we see is the latency for NOC, it increases very slowly, whereas for, and it looks like it's almost linear, but for OCC, it just increases. The more clients you have, the more contention, and the store has to process all of these transactions and just can't keep up. So where's this performance benefit? Where's it coming from? Here, what we plot is the number of clients versus the aborts per transactions from the store. So this is the number of, essentially the number of retries, or the number of transactions that are the number of retries a transaction has to go through before it's committed on the store. So with OCC, as we increase the number of clients, the store wastes a lot of time trying to commit transactions. With NOC, however, almost all the transactions that are received by the server are committed. This means that the server is only executing useful instructions that actually commit transactions. Then we tried running this with TPCC. So TPCC is a benchmark for databases, and we evaluated the payments transaction, which is a transaction with lots of contention. And what we found for this this benchmark, running in this case for payments, we plotted the CPU usage at the store. And with OCC, as the number of clients increases, the amount of contention increases, so the store has to validate more or abort more transactions. However, with NOC, at the stores, the CPU usage doesn't increase as much. This is because, yes, there are more transactions arriving, so the usage increases, but since the useless transactions, the transactions that will be aborted, are not sent to the switch, or excuse me, to the store. Instead, they're processed by the switch and aborted earlier in the network. This reduces the overall load on the store. And at the same time, it doesn't have a significant effect on the throughput. So it reduces the load on the store, but at the same time, it doesn't have any performance penalty for the benchmark, which is something that we would hope. So overall, with NOC, we can offload this transaction verification and put it on a switch, which is running in the network. And actually, these programmable switches are already deployed. They're in last year. There were some announcements about these being deployed in data centers. I think AT&T is running these switches in their network. So these are real devices that are already being used. And with NOC, we can reduce, using these devices, we can reduce the throughput for these workloads that have high contention. And because we're using OCC, it doesn't have any negative impact on low contention workloads either, as we saw that OCC works very well for low contention workloads. And not only does it increase throughput, but NOC also reduces the load on the server by offloading it to these switches. So I'll take any questions, and thank you for your attention.
Questions? Actually, I have a question if there's nobody to ask. So I was thinking what happens when clients can update or access the data store on multiple paths. So what does your network cache do in this case? Like, do you update them consistently, or do you have any idea or proposed solution for that?
So in terms of correctness, there's no problem if clients access the store from different paths, but they just won't benefit from the verification offload if they had access the store through the switch. So if these are, for example, you may think that the state of the cache on the switch will be out of sync with the store, but as you saw, if the store aborts a transaction, so let's say that the switch is out of sync and the switch allows a transaction to go through, that transaction will be aborted and the abort message will contain the up-to-date value. So the switch will resync with the store and eventually allow transactions through.
Okay, let's thank the speaker. Okay, our last speaker of the session is Thomas Kohler. Thomas received his master's degree from Augsburg University in Germany, and he's currently pursuing his PhD in the Distributed Systems Research Group at the University of Stuttgart, Germany. His research interests include consistency and determinism in software-defined networking, as well as white box and programmable networking hardware. So thank you, Thomas.
Thank you very much for the kind introduction. The taskbar won't disappear. I'm sorry for that. Let's hope eventually it will disappear. I hope we can live with that. So today it's my pleasure to introduce our work called P4CEP towards in-network implementation of complex event processing, and this is joint work with my colleagues from the University of Stuttgart. So what is complex event processing about? The goal of complex event processing is to infer the occurrence of situations of interest based on basic events. In this example you see here, there are networked temperature and smoke detectors, and they send basic events, that is the temperature and whether smoke is detected or not, to a CEP operator, and based on these basic events, the operator would detect fire and would send it to an extinguisher system, for example. The way that CEP is implemented these days is that these operators are implemented in software on off-path hardware, following the middlebox model, and through this XC2 processing there is additional latency because that hop to the external C operator causes latency, obviously, and through the software processing we also have limited throughput. Now this basic example does not seem to be most latency critical, but typically real-world CEP applications are, if you think of inferring leading market signals based on stock quotes, for example, or high-frequency trading or network control where you want to react on detected intrusions or network failures. Furthermore, you note that the sources and sinks of these events are inherently distributed, and typically also to increase throughput, the COP operators are distributed in a graph of operators. Now what we propose is to implement CEP within programmable or reconfigurable data plane hardware, and through this in-situ processing there is no additional round-trip times involved, and this decreases latency significantly. And through the processing in hardware, we are also gaining higher throughput. And the benefit of using a uniform data plane programming language for that is that portability is much increased. So our contributions are as follows. We present concepts for the in-network implementation of complex event processing, and in particular, we present a rule specification language as well as a compiler that takes this rule specification language, the rules that are specified in this language, and compiles it to P4 code. Then we're going to present our proof of concept implementation of this P4CEP compiler, which has targets a programmable NICs. So these are the metronome network framework, the network flow processor framework, and a software switch, BMB2. And this is open source, so you can have a look at it. Furthermore, we discuss our experience and encountered limitations in stateful packet processing using data plane programming. And we show our evaluation on a programmable NIC and conclude with a roadmap towards the distribution of in-network CEP. So let's come back to CEP for a minute. As said, the main goal of CEP is to infer the occurrence of situations of interest, and in doing so, a CEP operator processes streams of incoming events and detects a complex event. And to specify these complex events, an event specification language is used that specifies conditions or expressions for when complex events are to be detected. And typically this consists of predicates on the actual values of these basic events and logical operators for the combination of multiple input streams. In the example you see here, the complex event fire would be detected if the temperature is larger than 50 degrees Celsius and there is smoke detected. And you note that in order for this to work, the CEP operator has to store the last seen basic events. However, it is much more interesting to be able to reason over a history of past events. And since these input streams are possibly infinite, these sequences are split into windows, and by that bounding the state. You see an example here of a so-called sliding window. It has a size and a slide that determines by how much the window proceeds. And you can use aggregation functions over these windows and use them in an expression for the pattern to detect. For example, here you could specify that the average temperature over the window should be larger than 55 degrees Celsius, and at least 3 times you have seen the smoke detection. Now, the requirements on processing in a data plane are as follows. We need, of course, memory for storing this limited event history. So that requires stateful processing in the data plane. And we need some processing logic for evaluation of expressions and window operators. So this is the system model of P4CEP. We're looking at 2 classes of end systems. The ones are the CEP end systems. They consist of CEP sources, which emit basic events, and CEP sinks, which receive complex events. And the other class of end systems is just ordinary end systems that just communicate with each other using packets. And these packets and basic events reach our P4CEP targets where they're handled accordingly. And then we have, of course, on the control plane, a runtime component, which basically monitors these CEP targets and updates them. So this is how the processing actually works within one of these P4CEP targets. First of all, the ingress traffic is classified, and it's classified, as said, into ordinary packets or basic events or complex events. And to discriminate ordinary packets from basic events, we use P4's very flexible parser. If packets coming that are not basic events or that are complex events that are just to be forwarded, we apply a so-called co-network function block, which just does forwarding and all other non-CEP related network functions. If the packet is to be handled by the CEP engine, in case it is a basic event, we do process it in sequential manner in 2 steps. First of all the window operations are executed. That means that the current value of the basic event is stored in the window, and these aggregation functions are evaluated. And then second, we execute a state machine for pattern detection. We're going to have a look at that now. And in case we detect a complex event, we use the resubmission mechanism to have it forwarded to its final sync. So just briefly, this is how the compile time workflow looks like. I won't go into the details, you will find it in the paper, but you'll notice that to the right side, we just use an unmodified P4 compiler chain. And on the left side, you see that we give the event header definition and the rules and patterns to detect to our P4CEP compiler, which then creates P4 code. And we currently support P4 version 14 and P4 version 16, and as said, the targets, and netronome target and software switch target. Furthermore, you'll notice that we make use of these external functions. These are the small blocks to the right, by using capabilities that are not covered within the P4 standard, and in particular, we're using that for window evaluations in the NFP framework. So the rule specification language consists of 2 parts. It consists of the definition of windows and the definition of complex events to detect. You see an example here, but we'll go step by step through it. So for the window operators, you see a definition, an example to the right. You can give it a name, obviously, and you determine the size of the window, and you specify a value that is to be stored within these windows. And this could be any valid packet header or metadata field. The currently supported aggregation functions are maximum, minimum, sum, and count. And for reasons that we've heard today, we heard earlier, we leave average for future work since there is no division operator and either floating point support in P4. We implemented window operations by storing the actual values in a ring buffer along with a pointer to the current index in that buffer, and use P4 registers for that. You'll note here that we have to register to isolate the access to those registers by confinement in critical sections. Otherwise, we will run into the risk of getting inconsistency effects like lost updates and so on. For our work, we use the metronome-given mechanisms for that. That is the preprocessor pragma and the C mutex library. In P416, there is the atomic control flow block. Now I have to mention that all these mechanisms are target dependent. So it's easier for this programmable smart NICs. It's harder for data plane switches. However, Sivaraman and al. Show that in fact there are hardware designs that offer these packet transactions, so hardware designs for actual data center switches. Now, after storing the current value in this ring buffer, we evaluate the aggregation functions. We do that by unrolling iteration over the window manually or explicitly, since there is no loop construct in P4. And unfortunately, we can't apply arithmetic operations directly on registers. That is why we have to use transient metadata fields that store the current aggregate value, the current index variable, and the value at the current index, and then apply the arithmetic operations on that. This is how a complex event is defined. You can, of course, again give it a name. The value here depicts the return value in case a complex event is detected. An example here, it would just sum up over the total length of IPv4 field. Then there is a strategy, which is either skip till next match or strict. We will see in a minute what that means. And you specify the pattern. And the pattern basically is any valid P4 expression. In our case, we use a simple or a compound predicate on basic events for that. We implement a pattern detection by a deterministic finite state machine. And as you can see here, as said, the pattern definition consists of basic events. These are input symbols to our state machine. And such a basic event typically consists of predicates on field references, that is either packet header values or metadata values, as well as window aggregates. And we use logical operators like sequence or conjunction or disjunction to combine predicates. And you see also an example here, and this example would read as the following. It would look at a basic event that is encoded as a large HTTP request or response, and that is followed in sequence by a second basic event, which would be either the sum over such a window exceeding a certain threshold or the ingress of a UDP datagram. You'll notice here that this example is from the networking domain, but it could be arbitrary events encoding arbitrary values. You see here the corresponding state machine on the bottom, and the actual strategy, transition strategy, determines what happens if there is an input symbol that does not lead to a transition. These are these else branches, and depicted here is the skip till next match strategy. The strict strategy would result in the transition to the initial state whenever there is an input symbol that is not part of the pattern occurring. Here you can see the actual implementation of the state machine in terms of table entries. So this is what our tables look like. And the actual transition is executed by using metadata fields that are storing the current state, which we read from a register, as well as the match predicate. And we use this pair of values as a key for the lookup in this transition table. And the next state given by this lookup or returned by this lookup is persisted in a register for the ingress of upcoming basic events, simple events. If it is not an accepting state, if it is an accepting state, we reset a state machine by setting the current state to the initial state, return or put the return value into the packet, and use the resubmission mechanism to have it sent out to the sink. So briefly, these are our encountered limitations, and the most important of all is the synchronization of state memory access, which causes additional latency if you use the primitives, if you have the primitives at all. For the NFP, we have measured around 700 nanoseconds per critical section additional latency. And as we have heard today, there are the language-dependent limitations, such as that registers cannot directly be referenced by arithmetic operations, or as table keys, you have to load them in a metadata field and then use them. There is no floating point arithmetics, no division operator. You could use fixed point arithmetics to fix that, and there is no loop construct, so you have to manually unload the rules. They're not even bounded loops, which would be a nice idea, I guess. Now we come to our evaluation and our results. Briefly for the methodology, we have looked at one complex event pattern consisting of two basic events, and we used the sum over a window of varying size n for that. Then, as you can see, we measure the egress timestamp of that second event that triggers the complex event detection, and we measure the ingress of the complex event. And this gives us the target processing latency, and we also measure throughput by that. Now here are the results. You can see we have evaluated NFP, this is the pure P4 implementation on a Netronome SmartNIC, as well as NFPC, and here we use the C sandbox of NFP for the window operations basically. And you will notice that this is necessary, otherwise we cannot go over window sizes of 10 with the pure P4 implementation. If we want to have larger windows, we have to use the C construct. You will further notice that the overhead of using this external function mechanism is quite bearable. And with NFPC, we look at processing latencies between 9.8 microseconds up to 30 microseconds from window sizes from 0 to 20. And throughput is about 56% to 16%, which translates to 8.3 million events per seconds to 2.3 million events per second for 10 gigabit Ethernet links. Furthermore, we have verified that the processing latency scales linearly with the window size up to a size of 1000. And for a quick comparison, we have put the numbers of the BMV2 implementation here as well, which is not optimized at all, so this just gives a rough reference. And there we're looking at latencies between 512 milliseconds and 10 microseconds, and 10 milliseconds over this range of window sizes. We have, however, measured the processing latency of a standard off-the-shelf software-based CEP system, Apache Flink, and there we're looking at around 200 microseconds of processing latency, but this is just for processing. This does not include the network delay, which we get because it's a remote box. Right? So to conclude, we have presented and introduced you to complex event processing and have laid out the requirements on its processing in the data plane. We have presented our network, our work on in-network implementation of complex event processing called P4CEP. We have also discussed and encountered limitations of data plane programming for stateful packet processing, and we have shown P4CEP's practicability on a programmable NIC target, yielding microsecond and million messages per second scales. Now for future work, we would like to look into the distribution of in-network CEP. And one thing we look at is where we can place these operators. We not only can place them in switches or at the programmable NICs in the end host, but we can also place them back again in software, where we can either target kernel processing, like with eBPFs, or using DPDK for user space processing. And the benefit here is that expressiveness is much broader. So we have a much more generic sense of processing here. However, this would need mechanisms and concepts for the replication and partitioning of events. And a second work we're looking into is to filter out unnecessary events in the network. Thank you very much for your attention, and I'm happy to take questions.
Questions?
I'm curious about the implementation of the state machine. You presented it as a single table. How do you traverse the state machine if it's in one table? And
so yes, it is within one table, and we just use the matching functionality, right? So we have this input, this pair as input, which holds the current state and the match predicate, which we encode as an ID. and then we just apply this as a key for the lookup in the table and get a pair back, which consists of the next state or whether this is an accepting state or not.
But to transition from one state to the next,
Yes.
how do you need multiple tables?
The transition itself depends on two things. Well, if it is an accepting state, we just handle the detection of the complex event, right? And then if it's not, we just persist the next state in a register and wait for the next basic event to enter the switch, and which would then be handled according to the updated state. Thank you.
That's the end of the NetCompute portion of the workshop. In the afternoon, there'll be the kernel bypass section of the workshop. Hope you all can attend.